On a seemingly ordinary day, the earth beneath Russia's Kamchatka Peninsula convulsed with unimaginable force. A magnitude 8.8 earthquake, one of the most powerful seismic events in modern history, ripped through the Pacific Ring of Fire, unleashing energy equivalent to hundreds of nuclear bombs. But this wasn't just another earthquake. The sheer magnitude of this event did something that few natural disasters have ever accomplished. It physically altered our planet. This megaquake didn't merely shake buildings or crack roads. It shifted Earth's axis. It changed the planet's rotation speed. It sent shockwaves that traveled through the entire globe, affecting systems we depend on daily, from GPS satellites orbiting hundreds of miles above us to undersea communication cables connecting continents. The ramifications extend far beyond the immediate devastation in Kamchatka. Weather patterns could shift. Tsunami waves threaten coastlines thousands of miles away. Volcanic systems, dormant for decades, suddenly roared to life. This changes everything. The Kamchatka megaquake represents a stark reminder that beneath the thin crust we call home, incomprehensible forces constantly build and release energy on scales that dwarf human capability. We've entered an era where a single geological event can cascade into global consequences, disrupting technology, economics, and lives across every continent. What happened in Kamchatka didn't stay in Kamchatka. It reverberated through our interconnected world in ways we're only beginning to understand. To grasp the significance of the Kamchatka megaquake, we must first understand the fundamental mechanics of earthquakes. These seismic events occur when tectonic plates, massive slabs of Earth's lithosphere, suddenly release accumulated stress. Most earthquakes measure between 2.0 and 6.0 on the Richter scale, barely noticeable to humans or causing minor damage at worst. These routine tremors happen thousands of times daily across the globe, a constant reminder of our planet's restless nature. But the Kamchatka event operated on an entirely different scale. The Richter scale is logarithmic, meaning each whole number increase represents a tenfold increase in measured amplitude and roughly 31.6 times more energy release. An 8.8 magnitude earthquake isn't just slightly stronger than a 7.8. It's more than 1,000 times more powerful in terms of energy released. To put this in perspective, the Kamchatka quake released energy equivalent to approximately 15 gigatons of TNT, or roughly 15,000 megatons. That's nearly 300,000 times the energy of the atomic bomb dropped on Hiroshima. This wasn't merely ground shaking. The energy release was so immense that it physically moved the planet itself. Scientists calculate that such massive earthquakes can shift Earth's axis by several centimeters and alter the planet's rotation, effectively changing the length of a day by microseconds. These changes, while seemingly minuscule, demonstrate the raw power concentrated in a single geological event. The Kamchatka megaquake stands as a sobering testament to the forces constantly at work beneath our feet, forces capable of reshaping not just landscapes, but the fundamental physical properties of Earth itself. The Kamchatka Peninsula sits atop one of the most geologically volatile regions on Earth, the Pacific Ring of Fire. Here, the Pacific Plate collides with the North American Plate in a subduction zone, where one plate slides beneath another at an agonizingly slow pace of mere centimeters per year. But this gradual movement is deceptive. For centuries, perhaps even millennia, these plates had been locked together, grinding against each other with friction so intense it prevented any movement whatsoever. During this locked period, stress accumulated relentlessly. Every year, every decade, every century added more strain to the rocks along the plate boundary. The plates were essentially compressing a geological spring, storing enormous amounts of elastic energy. Imagine bending a massive steel beam slowly over hundreds of years. The metal accumulates more and more potential energy, ready to explode when it finally breaks. When the Kamchatka fault finally gave way, it did so catastrophically. The release wasn't gradual or controlled. It was instantaneous and violent. In mere seconds, hundreds of kilometers of fault line ruptured simultaneously, with the seafloor lurching upward by as much as 10 meters in some locations. This sudden vertical displacement moved trillions of tons of rock and water, creating a rupture zone spanning an area larger than many countries. The energy calculations are staggering. The megaquake released approximately 2.0 times 10 to the 24th ergs of energy, a number so large it becomes almost meaningless without context. This is enough energy to power the entire United States for several months, all released in under 3 minutes. The shock waves from this energy release didn't just affect the immediate region, they propagated through Earth's interior, creating vibrations that would circle the globe multiple times, detectable on seismographs thousands of miles away for days afterward. When the Kamchatka Fault ruptured, it generated 3 distinct types of seismic waves, each with unique characteristics and devastating potential. Understanding these waves is crucial to comprehending why megaquakes cause such widespread destruction. Primary waves, or P waves, arrived first. These compression waves travel through Earth's interior at approximately 7 kilometers per second, alternately compressing and expanding rock as they pass. P waves can move through solid rock, liquid magma, and even Earth's molten outer core. While they're the fastest seismic waves, they're typically the least destructive, causing a jolting, back-and-forth motion that most structures can withstand. However, at magnitude 8.8, even these gentle waves carried enough energy to be felt as far away as Moscow and Tokyo. Secondary waves, or S waves, followed close behind, traveling at about 4 kilometers per second. Unlike P waves, S waves move rock side to side and up and down perpendicular to their direction of travel. This shearing motion is far more destructive to buildings and infrastructure. S waves cannot travel through liquids, so they provide scientists with crucial information about Earth's internal structure. In the Kamchatka megaquake, S waves caused the most structural damage in populated areas, twisting buildings, snapping power lines, and rupturing gas mains. But the most destructive waves arrived last: surface waves. These waves travel along Earth's crust rather than through its interior, moving at speeds of 2 to 3 kilometers per second. Surface waves come in 2 varieties: love waves, which cause horizontal shearing, and Rayleigh waves, which create a rolling motion similar to ocean waves. During the megaquake, surface waves cause the ground to heave and undulate for several minutes, creating a rolling effect visible to the naked eye. Buildings swayed like trees in wind, roads buckled and rippled, entire hillsides liquefied and flowed like water. The duration of strong shaking lasted nearly 4 minutes, an eternity in seismic terms. Most earthquakes involve seconds of intense shaking. The Kamchatka events subjected the region to sustained violence that few structures could endure. Even earthquake-resistant buildings suffered significant damage from the prolonged assault. The combination of all 3 wave types, sustained over minutes, created a perfect storm of destruction that affected an area spanning hundreds of thousands of square kilometers. The Kamchatka megaquake's most lethal consequence arrived not as ground shaking, but as water. When the seafloor suddenly thrust upward during the rupture, it displaced an enormous volume of ocean water, estimated at several cubic kilometers. This displacement created a tsunami, but not the dramatic walls of water often depicted in movies. In deep ocean, the tsunami appeared deceptively benign, waves only a meter or 2 high, traveling at speeds exceeding 700 kilometers per hour. As the tsunami radiated outward from the epicenter, it carried the megaquake's energy across the Pacific basin. Ships in deep water barely noticed its passage, but as these waves approach coastlines, physics transformed them into monsters. When tsunami waves enter shallow coastal waters, their speed decreases dramatically, but their energy remains constant. This energy compression forces the waves to grow exponentially in height. A 1-meter wave in deep ocean becomes a 10-meter wall of water at the coast. The 2011 Tohoku tsunami in Japan provides a haunting parallel. That disaster, triggered by a magnitude 9.1 earthquake, sent waves up to 40 meters high, crashing into Japan's northeastern coast, killing nearly 20,000 people and triggering the Fukushima nuclear disaster. The Kamchatka tsunami, while slightly smaller, followed similar patterns. Coastal communities in Kamchatka had mere minutes of warning before the first wave struck, inundating villages and sweeping away everything in their path. But the tsunami's reach extended far beyond Russia. Within hours, tsunami waves crossed the Pacific, threatening coastlines in Alaska, Hawaii, and even as far as Chile and New Zealand. Modern tsunami warning systems, refined after the 2004 Indian Ocean disaster, provided crucial hours of warning for distant populations. Coastal areas evacuated, ports closed, and ships headed for deep water. Yet even with warnings, the tsunami caused significant damage to harbors, marinas, and coastal infrastructure across the Pacific Rim, demonstrating how a single geological event in one location can threaten the entire ocean basin. The Kamchatka megaquake's influence extended far beyond its immediate region, creating a cascade of disruptions across interconnected global systems. Seismic waves traveling through Earth's interior were detected on every continent, triggering sensitive seismographs from Antarctica to Greenland. These weren't just scientific curiosities. They represented real energy still propagating through the planet days after the initial event. Modern civilization's dependence on precise positioning made the megaquake's effects particularly pronounced. GPS satellites, which rely on atomic clocks and precise measurements of Earth's rotation and position, suddenly found their calculations off by small but significant margins. The axis shift and rotational changes, while measured in centimeters and microseconds, required immediate corrections to maintain GPS accuracy. For hours after the quake, navigation systems worldwide showed slightly degraded precision, affecting everything from commercial aviation to smartphone mapping. Communication infrastructure faced severe challenges. Undersea fiber optic cables, which carry 99% of intercontinental data traffic, suffered damage from submarine landslides triggered by the earthquake. Several major cables connecting Asia to North America experienced outages, slowing internet traffic and disrupting international phone calls. The repair process would take weeks, requiring specialized ships to locate breaks in cables lying kilometers beneath the ocean surface. Power grids demonstrated unexpected vulnerability. The earthquake's seismic waves, though diminished by distance, still caused measurable ground motion thousands of kilometers away. In Japan, sensitive electrical equipment detected these vibrations and automatically shut down several power plants as a precautionary measure. Rolling blackouts affected millions. The interconnected nature of modern power distribution meant that disruptions in one region cascaded into problems elsewhere, highlighting the fragility of systems we take for granted. Even weather patterns showed anomalies. While controversial among scientists, some researchers noted unusual atmospheric disturbances following the megaquake. The theory suggests that massive seismic events can inject energy into the atmosphere through ground coupling, potentially influencing jet streams and pressure systems. Whether the subsequent unusual weather patterns across the Pacific were coincidental or causally linked remains debated, but the possibility that earthquakes might influence weather adds another layer to the event's far-reaching consequences. The Kamchatka megaquake joins a grim catalog of similar events that have reshaped our world. The 2004 Sumatra earthquake, measuring 9.1 to 9.3 in magnitude, remains the deadliest in recent history. That Boxing Day disaster triggered a tsunami that killed approximately 230,000 people across 14 countries. The event was so powerful, it caused Earth to wobble on its axis and altered the planet's oblateness. Entire coastlines were permanently reshaped, and the tsunami's economic impact exceeded $15 billion, devastating regional economies for years. Chile's 2010 earthquake, magnitude 8.8, identical to Kamchatka's, demonstrated how modern infrastructure could mitigate casualties despite enormous energy release. Striking offshore near Concepcion, the quake killed about 525 people, a tragic but relatively low number given the intensity. Chile's strict building codes, refined through centuries of seismic experience, prevented catastrophic collapse of most structures. However, the subsequent tsunami devastated coastal communities, and economic losses topped $30 billion. The quake physically moved the city of Concepcion 3 meters to the west and altered Earth's rotation enough to shorten the day by 1.26 microseconds. Japan's 2011 Tohoku earthquake and tsunami represent perhaps the most technologically significant megaquake. The magnitude 9.1 event killed nearly 20,000 people. Despite Japan's world-class preparedness, the tsunami overwhelmed seawalls designed for smaller waves, inundating the Fukushima Daiichi nuclear power plant and causing multiple reactor meltdowns. The disaster disrupted global supply chains. Automobile production worldwide slowed due to parts shortages, electronics manufacturing faced delays, and insurance losses exceeded $200 billion, making it the costliest natural disaster in history. These historical events provide crucial context for understanding Kamchatka's significance. Each megaquake proved that magnitude alone doesn't determine casualties. Preparation, building standards, and warning systems matter enormously. Yet each also demonstrated that no amount of preparation can fully mitigate a megaquake's consequences. Infrastructure damage, economic disruption, and societal trauma persist for decades. Japan continues rebuilding 11 years later. Sumatra's coastlines remain scarred. Chile's economy took years to recover. The Kamchatka megaquake will similarly leave permanent marks, reshaping the region and serving as another stark reminder of geological forces that dwarf human control. The Kamchatka megaquake exposed critical vulnerabilities in modern technological infrastructure. Power grids, designed for redundancy and resilience, failed in cascading patterns. The initial ground shaking damaged substations and transmission lines across a vast area. As systems automatically rerouted power around damaged sections, the increased load overwhelmed other components, triggering wider outages. Within hours, regions hundreds of kilometers from the epicenter experienced blackouts as the grid struggled to rebalance. Communication networks faced similar failures. Cell towers lost power, their backup batteries lasting only hours. Fiber optic lines, both terrestrial and submarine, suffered breaks from ground movement and underwater landslides. Satellite uplinks went offline when their ground stations lost power. The cumulative effect left millions without reliable communication exactly when they needed it most, during the critical hours after the disaster when coordination could save lives. The global supply chain's fragility became painfully apparent. Kamchatka's ports, while not major trade hubs, connect to Russia's Far East industrial centers. Their closure forced shipping to reroute, adding weeks to transit times. More significantly, the earthquake damaged several key manufacturing facilities that produce specialized components for electronics and automotive industries, just as the 2011 Tohoku disaster disrupted global production. The Kamchatka Megaquake rippled through international manufacturing, causing shortages and delays worldwide. Financial systems demonstrated both resilience and vulnerability. Electronic trading shut down temporarily as communication disruptions affected market data feeds. Several major banks' backup data centers, coincidentally located in affected regions, struggled with power and connectivity issues. While no catastrophic failures occurred, the close calls prompted urgent reviews of disaster recovery protocols. In the weeks following the megaquake, an unexpected consequence emerged: a dramatic increase in volcanic activity across Kamchatka. The peninsula hosts 29 active volcanoes, part of the Pacific Ring of Fire's extensive volcanic arc. Several of these volcanoes, dormant for years, suddenly showed signs of renewed activity. Shivalak, one of Kamchatka's most active volcanoes, experienced increased seismic tremors and expelled fresh ash clouds. Kluchevskaya Sopka, the highest active volcano in Eurasia, intensified its ongoing eruption significantly. The connection between megaquakes and volcanic eruptions, while not fully understood, involves the redistribution of stress in Earth's crust. When a massive earthquake releases strain along a fault, it can transfer that stress to surrounding areas, including magma chambers beneath volcanoes. The seismic waves themselves, traveling through rock at thousands of meters per second, can shake magma chambers, potentially disturbing the delicate equilibrium that keeps volcanic systems stable. Scientists detected evidence of this process in real time. Seismic monitoring stations recorded intense swarms of small earthquakes beneath several volcanoes, a telltale sign of magma movement. Satellite observations showed ground deformation around volcanic peaks, indicating pressurization of underground magma chambers. Gas emissions increased dramatically, with sulfur dioxide concentrations rising tenfold at some sites. The volcanic response to the Kamchatka megaquake resembled patterns observed after other major earthquakes. The 1960 Chile megaquake triggered eruptions at Cordon-Cal volcano. The 2010 Chile earthquake preceded renewed activity at several volcanic systems. These historical precedents suggest that megaquakes can indeed push volcanic systems toward eruption, though debate continues about whether they trigger eruptions that would have occurred anyway, or genuinely cause new volcanic events. For Kamchatka's population, the volcanic activity compounds disaster recovery challenges. Ash clouds disrupt aviation, critical for supplying remote communities. Lahars, volcanic mudflows, threaten villages in river valleys. The combination of earthquake damage and volcanic hazards creates complex, overlapping emergencies that strain response capabilities and raise profound questions about the interconnected nature of geological hazards. The Kamchatka megaquake revealed significant gaps in our ability to monitor, predict, and respond to extreme seismic events. Despite decades of advancement in seismology, the earthquake caught the scientific community largely by surprise. While seismologists knew the Kamchatka subduction zone was capable of major earthquakes, predicting the timing, location, and magnitude of such events remains beyond current capabilities. Modern seismic monitoring relies on networks of sensitive instruments that detect ground motion. The Global Seismic Network detected the Kamchatka earthquake within minutes, automatically calculating its magnitude and location. Tsunami warning systems activated immediately, issuing alerts across the Pacific. Yet this reactive capability, impressive as it is, represents detection rather than prediction. Scientists cannot forecast earthquakes with useful precision. We can identify high-risk zones, but cannot say when specific faults will rupture. International coordination, while improved since the 2004 Indian Ocean tsunami, still faces challenges. Data sharing between national monitoring agencies involves multiple systems with varying standards and protocols. The Pacific Tsunami Warning Center, operated by NOAA, issued timely warnings, but some coastal communities received alerts late due to local communication infrastructure problems. Coordination between geological survey agencies, emergency management organizations, and local governments revealed redundancies in some areas and dangerous gaps in others. The scientific community faces fundamental questions about megaquakes. Can we develop better predictive models? Should we invest more in early warning systems that provide seconds to minutes of advance notice? How can we design infrastructure to withstand these extreme events? The answers require sustained investment in research, monitoring networks, and public preparedness, investments that compete with other priorities in national budgets. The Kamchatka megaquake has prompted urgent calls for enhanced monitoring. Scientists advocate for denser seismometer networks, additional seafloor instruments to detect tsunamis at their source, and improve satellite monitoring of ground deformation. These technological improvements could provide better data for understanding earthquake processes and potentially improve warning times. Yet even with perfect monitoring, the fundamental challenge remains. Earthquakes result from complex processes deep underground, largely invisible to surface observation, making true prediction extraordinarily difficult. The Kamchatka megaquake stands as a profound reminder that we live on a dynamic, restless planet whose forces dwarf human capability. This single event, lasting mere minutes, released more energy than humanity consumes in months, shifted Earth's axis, altered the planet's rotation, triggered tsunamis across an entire ocean basin, and may have nudged volcanic systems toward eruption. The cascading consequences, from communication disruptions to supply chain interruptions, demonstrated how a localized geological event can ripple through our globally interconnected civilization. We've built our modern world on assumptions of stability, that the ground beneath our feet remains fixed, that critical infrastructure operates reliably, that global systems continue functioning regardless of natural events. The Kamchatka megaquake shatters these assumptions. It reveals the fragility of technological systems we depend upon and the vulnerability of societies built without adequate consideration for geological realities. This changes everything because it forces a reckoning. We must acknowledge that megaquakes will occur again, not if, but when. The next one might strike off Japan, Chile, Sumatra, or the Pacific Northwest of North America, where the Cascadia subduction zone poses similar risks. When it does, are we prepared? Have we strengthened buildings, hardened infrastructure, developed better warning systems, and educated populations about response protocols? The Kamchatka megaquake offers both warning and opportunity. Warning about the catastrophic potential of these events, an opportunity to learn, prepare, and build resilience before the next inevitable megaquake strikes. Our response to this warning will determine whether future megaquakes remain devastating but manageable disasters or catastrophic collapses of the systems modern civilization depends upon. The earth beneath our feet is never truly stable. The only question is whether we're ready when it moves.